Okay, finally, now that we've covered transposition and inversion, we're going to move on to that situation I was talking about at the beginning of the first video, which is what happens if our set class, the set class that's being used, is symmetrical. Okay, if we're dealing with a symmetrical set, as we're going to find out towards the end of this, that means we're going to have to look for multiple mappings. All right, so this is really important because, you could easily be misled in an analysis. You might immediately go towards one answer, but maybe if it's a symmetrical set class, you may need to think of multiple answers, and then there's a whole bunch of repercussions, really, if the composer is using a symmetrical set. Anyhow, first let's talk about just kind of what this means. Now, some of this will be familiar from what we learned in Bartók, but now we're going to use some of the language we've developed with pitch class set theory to talk about symmetrical sets. So the definition of a symmetrical set, this would be a set that has a palindromic interval series. Probably another way to look at it would be you can draw a line of symmetry. But so notice that this set has the interval series 2, 1, 2. So that's a symmetrical series 2, 1, 2. Whereas this set here has the interval series 2, 2. That's also symmetrical, right? 2 to 2. So it reads the same way front and back. Boy, it will be nice. Again, there's some, normal order usually gives you what you need, but occasionally you will have to shuffle the notes to see this palindromic pattern. 027, which you may remember is the stack of perfect fourths or fifths. This would need to be reordered as 270 to show the 5-5 pattern. So again, occasionally the normal order or even the prime form won't give that away. But the one thing that is definitely always a giveaway would be that you can draw a line of symmetry on the clock face. That would tell you have a symmetrical set. Now, there are two types of symmetry that we might talk about. The first one is the one that you all are familiar with, which is what we talked about with Bartók. And this would be inversional symmetry. Okay, so one type of symmetry is inversional symmetry. The way that this is worded in terms of set theory is it means that the set can invert onto itself. Now, that may be a little bit confusing, but essentially it means that if you kind of draw the line of symmetry and you apply that, you would get the same notes back if you invert it around that axis of symmetry. So it can invert onto itself. I wouldn't worry too much about that, though. I would more think about that, how many lines of symmetry you can draw. Yeah, on the clock face, you will be able to draw one or more lines of symmetry about which the pitch class is balanced. That would be, to me, the big giveaway for inversional symmetry, if I can draw some lines of symmetry, just like we did with Bartók. Also, the normal order might give some things away. If you sum the pitch classes from the outside to the inside, you'll get the same sum, like right up here. 1 and 6 sums to 7, 3 and 4 sums to 7. So that tells you have a symmetrical set class. Over here, 2 and 6 sums to 8. And then you got to do it on its own. 4 and 4 sums to 8. That will be another giveaway. It just depends what you kind of have in front of you that you're dealing with a symmetrical set. For example, if we take one symmetrical set, 024, on the clock face, you'll be able to draw one line of symmetry. If I go over here and I put up 024, notice that I can draw a line of symmetry. I'm not sure if I can stabilize my hand enough to do this, but here to here, right? That shows you the notes balancing. This is just like what we did with Bartók. So that would be an indication of inversional symmetry, that I can draw some sort of line of symmetry. Or the axis. So that was through pitch class 8 and pitch class 10. So we're familiar with that with Bartók. And then same thing, if I sum from the outside in, I get 4s. 0 and 4 sum to 4, 2 and 2 sum to 4. By the way, I'm kind of moving back and forth between the normal order and the prime form here because it's the same kind of issue. When I'm thinking about set symmetry, I'm actually thinking in kind of an abstract sense. So I can use the integers from the prime form, or I can use actual integers like in a normal form or a normal order. All right, so that's inversional symmetry. Now the other one is new. This is something we have not discussed, and is a very special situation that a much smaller number of sets have, which is transpositional symmetry. This is where a set can transpose onto itself by different Tn levels. Now, I probably should have put this next, but all sets can map onto themselves by T0, right? That doesn't move any notes. That's a trivial case. It's going to be included later on in our degree of symmetry, but just know that that does not by itself mean it's a symmetrical set, but we do include that later on in the degree of symmetry. Now, anyhow, most of the T-symmetrical sets are really well known to you. They're the ones that Bartók loved to use, like the augmented triad, the diminished seventh chord, the whole tone scale, the octatonic scale, and so on. And these sets will also always be inversionally symmetrical. So T-symmetry is a special thing that certain sets have where they can transpose onto itself. Let me show you an example, one of the easier ones to see, the set 048. So 048. Now you'll notice we can draw a bunch of axes of symmetry here. I can draw a line, or inversional symmetry. I could draw a line right there. I could draw a line right there. And I can basically draw 3 lines of symmetry. So that's inversional symmetry. But what is transpositional symmetry? So besides T0, which of course would give us these same notes, you'll notice that if I also transpose, so T0, that's kind of the trivial case. I'll put that in parentheses just because we need it for our formula later on. But also, I can get these same notes again if I transpose by T4. Right? Notice if I kind of moved this and rotated it by 4 half steps, I get the same 3 notes again, right? 0 would go to 4, 4 would go to 8, 8 would go to 0. And then in addition, if I did T8, right? If I did T8, 0 would go to 8, 4 would go to 0, and 8 would go to 4. I get all the same notes again. So that's what transpositional symmetry is. It's much rarer, and it's, a really special case. And most of the ones that have transpositional symmetry, other than, of course, the trivial one, are really well-known things. It's like a special situation. So I think that's what I probably put over here. Yeah, T4 and T8, you'd also get the same. So we have the trivial case of T0. We also have T4 and T8. So that's an example of transpositional symmetry. All right, so now that we have these 2 types of symmetry, eventually we're going to get to the issue of mappings, but I need to describe this first before we get into this, because we're going to use the appendix of set classes to help you figure this out. All right, so now let's go on to the main thing here, which is the degree of symmetry. Now this is going to be found in the list of set classes, so I'd strongly recommend that you all have that printed out. This document that was in the last module. The degree of symmetry is found right here, this column here. So remember how in the list of set classes they gave you the Fort number, they gave you the prime form, they gave you the interval class vector, and then finally they give you the degree of symmetry. So this is, going to be, so anyway, what does this mean? The degree of symmetry is going to tell you in the first column how many ways the set can transpose onto itself. So first column is Tn values that, for example, 012 can transpose onto itself. And notice how there's always a 1 there because there's always T0. That does not mean transpositional symmetry. If you just see 1 over there, all sets have that. So that is just going to be included for a formula we're going to talk about in a little bit. And then as you probably imagined, this second column is Tni. How many ways this set 012 can invert onto itself. which probably a better way for you to think about is how many lines of symmetry can I draw for this set. So if you see 1, 0, those are non-symmetrical sets. That's all the stuff we were doing in the last 2 videos. That means that we don't have a symmetrical set, so don't be fooled by the 1 in the first category. So if you were dealing with sets that had just this, and they're non-symmetrical sets, then you would do all the stuff we talked about in the last video. But we're going to be really interested in the other ones, the one that have extra levels of symmetry. All right, so by the way, let me show you. Notice the ones that have some transpositional symmetry. They're very well-known sets. 048, the augmented triad. Let's see, I don't see any yet in the... I just look through this, and I want to see in the first column if I ever see anything different. Oh, here you go. This one, 0167, has a 2 and a 2. That means, by the way, this is the Z cell that Bartok loved to use. Let's see if there's another one. All right, here's another good one. 0268. That's another one composers like to use a lot. Oh, look at this one. The diminished 7th chord is extremely symmetrical. So it has 4 and 4 ways of both ways, and so on. If you keep looking down through the list of set classes, you'll find lots of well-known things like the whole tone scale, the hexatonic scale, the octatonic scale, and so on. All right, so let me take a look here. I think that probably I just mentioned everything right there that I was going to talk about. Yeah, I think I already described all of this stuff. So this was what I was just talking about a second ago, how to read the degree of symmetry. Now, why are we so interested in this? So this is my next point. Why is this information useful? Now, eventually it's going to be about mappings, but before that, there's another very important thing that we can do with the degree of symmetry, is it indicates how many distinct pitch class sets there are for each set class. Now remember how if it's a non-symmetrical set, there will be 24. There will be 12 going clockwise and 12 going counterclockwise. If we had 013, for example, which is non-symmetrical, there's 24 different sets that are 013s. But if we have a symmetrical set, it's going to be fewer because we're going to plug in this formula. And what you're going to do is do 24, which is the ultimate number that you can have for a set class, divided by the total degree of symmetry. For example, the set 048 has a degree of symmetry of 3, 3. So 6 things in total, right? Therefore, what you'll do is take 24, which is the ultimate, divide it by the total degree of symmetry, which here is 6 total, and you'll get 4. That means there's actually only 4 048s. We already knew that, though, didn't we? We already knew that there's only 4 augmented triads. So this is telling us some stuff we already knew, but it's using this kind of theory to figure that out. For example, let's look at another one, actually. Let me see if I can find the octatonic scale in the... see, somewhere in the octachords, we're going to have the octatonic scale. I'm guessing it's going to be 1, 2, 3, 4, 5. Yeah, here it is right here. So the octatonic scale, this is the set class of the octatonic scale. It has the degree of symmetry of 4, 4. Isn't it interesting that both this and this have the same degree of symmetry? We'll talk about why that is in a later lecture. It has to do with complementation. So if we take our formula then, 24 divided by the total number here is 8, and we get 3. So that means what we already knew, that there are only 3 octatonic scales, right? The octatonic 01, octatonic 1, 2, and octatonic 2, 3. Now, anyhow, all I've talked about so far was sort of abstract, learning a little bit about the degree of symmetry. It's pretty interesting, though, obviously, because remember, anytime a composer uses a symmetrical set, that means that we're dealing with, basically, it's going to limit the options, essentially. Limit the options in terms of how many pitch class sets you can get, but it's actually going to then expand the options for mappings. Okay, so now we're finally back to the issue of mappings between sets. The degree of symmetry if we're looking at a symmetrical set, also tells you how many mappings to look for between two sets of a given set type. Now, again, if it's a non-symmetrical set, we know to look for just one. But if it's symmetrical, then I know to look for multiple ones. And this is where things are going to get a little bit complicated. So again, if I'm looking at two different sets and they're both of the same set class, and the set class is symmetrical, I know I need to look for multiple mappings. So 1, 0 is not a symmetrical set. So there you just do what you did before. It's going to be either transposition or inversion. If, however, the degree of symmetry was 1, 1, you would look, if you were doing the mappings, you would look for one transposition and one inversion. You can actually read it that literally, 1 and 1. I'd look for one transposition and one inversion. I'll show you in a second. Whereas if you saw a situation where the set class was 2, 2 in terms of the degree of symmetry, I would look for 2 transpositions and I'd look for 2 inversions. Now, I know this is a little confusing because now I'm talking about mapping two different sets that are that particular set class. Up here, I was looking at just the set class by itself. But now I'm back to that issue of mappings. Okay, now let's go ahead and show you how you're going to do this. Now we're finally back to where I wanted to kind of reach this point. So here, I'm going to determine all the mappings between this set and this set. Both of them are prime form 012. All right, so as soon as you see this, you go, oh, they're both 012s. It's a symmetrical set, so I can't just look for one answer. I need to look for multiple answers. We could go through the long process of showing this, but really just, you can look at your list of set classes. And we saw that 012 had a degree of symmetry of 1, 1. That means I need to look for one transposition and I need to look for one inversion. So now that I know that I'm going to need to look for one transposition from this to this and one inversion from this to this, then I just plug in what I learned about transposition and inversion. Transposition, I'm looking for differences, right? 5 going to 2, I'd have to add 9, right? 6 going to 3, add 9. 7 going to 4, add 9. So one of these answers would be T9. So I figured out the transposition that I was looking for between these two sets. And then I now need to also look for an inversion though, because it was 1, 1. So with inversion, remember, I sum from the outside in to find the sum value. 5 and 4, 6 and 3, 7 and 2, and this is just a coincidence. It just so happens to be T9I. But remember, those numbers, the in values, mean something very different from a transposition and inversion. Okay, let me show you another one now. So let's say I asked you to figure out all the mappings from this onto this. It's the prime form 0167, the Bartok Z cell. All right, now let's take a look at our list of set classes. I think I showed you this one a moment ago. Let's look for 0167. Here it is. Degree of symmetry is 2, 2. Uh-oh. That means we need to look for 4 things in total. I need to look for 2 transpositions and 2 inversions. Okay, so this is going to be new. Let me show you what you're going to do in this particular case. Let's start by finding the easy ones, the ones where I don't need to reorder anything. So let's look for the transposition first. So 1 to 0. 2 to 1, 7 to 6, 8 to 7. Notice how each one is 1 less. That means T11, right? Because I have to go ordered. So one of the answers is T11. Now let's do one of the inversions where I don't have to reorder anything. I'm going to sum from the outside in. 1 and 7, 2 and 6, 7 and 1, 8 and 0, and it's 8, right? Sums of 8, so T8I. The problem is now I'm not done. I have to do more. I need now to figure out the other 2. I know that there's going to be one more transposition to look for and one more inversion. Now, what you need to do in that case is you need to just leave this set where it is. You leave it as kind of the basis and the foundation. Take the second set and reorder it. But you need to reorder it so that it has the same interval series that it has now. Right now, the interval series is 1, 5, 1. So I need to reorder this so that it has that same interval series, because that will then help me do the rest of this. So that would be 6, 7, 0, 1. This will be a reordering of this set that still has the 1, 5, 1 interval series. Okay, so 6, sorry, this is a little sloppy. 6, 7, 0, 1. Sorry, let me. Oh, come on. All right, back to this. All right, so just to say what I did there again, since I know I need to look for another transposition and inversion, I need to reorder the second set that in a way where I keep the 1, 5, 1 interval series. And now I'm going to do just what I did before to find these. So I'll find the transposition. 1 to 5 is 6, or sorry, 1 to 6 is 5, 2 to 7 is 5, 5 to 0 is 5, 8 to 1 is 5. So the other transposition is T5. And then the other inversion, remember with inversions, I sum from the outside in. 1 and 1 is 1, 2 and 0, 1 and 1 is 2, 2 and 0 is 2, 8 and 7 is 14 or 2, 8 and 6 is 14 or 2. So that's T2I, and there I go. So again, the whole issue of this was, this is really where I wanted to go with this particular video, is when you encounter the whole issue of how many mappings there are and the set class is symmetrical, there's extra work that's involved there. It's going to be more than one answer. Now, of course, then, and this is something I'm going to ask you on the homework, when you have like something like this with all these answers, if you look at a real musical example, they may not all be equally good analyses of the music. You have to kind of look at the music to decide which one seems to be a better analysis. Like if this happened, this to this in the music, and all the voices moved up by 5 half steps, then wouldn't T5 be the best answer? Even though these are also correct, this would be like the most accurate description. Whereas in other cases, it might not be so straightforward. Okay, so we'll be doing some more practice on this in class.